Okay, cool. So the data over the duration of the experiment provide the strongest support for which of the following conclusions regarding the effect of the parasite on tribolium populations. So this one is saying that confusum is adversely affected. So let's go up and look. And if you look at confusum, well, the difference between the parasite and not the parasite is, pretty much the same thing. So I'm going to cross that one out. That would be backwards. Castanium is adversely affected by the parasite while confusum is not. That is the one we want, because if you look at this one, here's the parasite and here's without the parasite. They have fewer number of beetles per culture dish with the parasite than they do without. So the parasite is definitely affecting them more. So that's one we're looking for. Let's look at both of them. Both of these populations are adversely affected by the parasite. That's not true because the confusum is not. And both of them show increased fitness in the presence of the parasite. Definitely not because this one has reduced fitness, right? When the parasite's around, it's not doing as well. Okay, number 5, in figure 1, so here's figure 1, and see how the lines are pretty much the same thing. The difference between the two curves can best be attributed to which of the following. This is one that my students typically have trouble with. The difference between laboratory controlled conditions and the natural environment. That's not it, because all of these were done in controlled conditions, right? It was all in petri dishes and culture dishes. So that one's not true. The effect of the host on parasite. I would say no to that one. That one might be true for the second one, but this isn't really showing a difference between the host and the parasite. So that's not the difference between the two lines. It would be for this one. The influence of competition for limited resources. Well, they're competing the same amount, whether it's, this one or this one. So that's not true. So what it's looking for is the natural variation among populations. So do you notice how the lines pretty much follow each other? Sometimes the without parasite is above, sometimes the with parasite is above. Here they separate just a bit. Here they swap places again a little bit, but the lines pretty much follow each other. So the difference between these populations is just probably a little bit of natural variation between populations. And that one, if you had trouble with this one, you are not alone. Okay, last one in this little set. If the experiment was continued for an additional 500 days, the population density of Castanium with the parasite would most likely stabilize at a value closest to which of the following? Okay, so the Castanium is the second one, and they said with the parasite. So, it hopped down a little bit here, but overall, it's kind of in this range. And so if I bring that over, that is somewhere, and it dropped a little here, somewhere around 10, maybe 15, something like that. And I hate this question because I don't think 20 is a super bad choice, but they're looking at 10. 5 seems a little bit, 5 would be down here, right? They never really got that low, right? So 5 would be, I didn't draw that very well, right here. And then 20 is up here. That's a little bit too high. Okay, number 7. Beaked whales feed at various depths, but they defecate, that means they poop, at the ocean's surface. Nitrogen-rich whale poop deposited at the surface supplies nutrients for algae that are eaten by surface-dwelling fish. So the algae are photosynthetic, but they use the nitrogen that's in the poop. They need some nitrogen. And then the algae are eaten by fish. Which of the following best predicts what would happen if the whale population decreased? So if you have fewer whale, then you're going to have less poop, which means less nitrogen, which means you'll have less algae, which means you'll have fewer of those fish, right? So there would be a reduction in surface nitrogen concentration, which would cause an algal bloom. That would be opposite, right? If you have less nitrogen available, you'll have fewer algae around. The surface fish populations would decline or decrease due to a reduced population of algae. That is what would happen. C, the remaining whales would accumulate mutations at a faster rate. That is just put in there to mess you up. Nobody's going to mutate at a faster rate unless that's advantageous, and it certainly wouldn't happen very fast anyway. The remaining whales would be forced to forage in the deepest parts of the ocean. That has nothing to with this question. There's no reason that they would go forage in a deeper part of the ocean just because there were fewer of them around. So be a little careful with these. Okay, number 8. Scientists have found that the existing populations of a certain species of amphibian are small in number, lacking in genetic diversity. Okay, that's a problem. If you don't have a lot of genetic diversity, that means you're more likely to die out, because if a virus comes along that attacks you, well, if everybody's exactly like you, everybody's going to get hurt if it hurts you, right? And the existing population, and separated from each other by wide areas of dry land. Okay, so we know amphibians live where there's water, and so if you have amphibians living here and here and here and here, and they're separated out by these dry areas, that means the ones here can't get over to the ones here, who can't get over to the ones over here. So that's bad for the population. It means they're more likely to become extinct. On the other hand, they are a little bit more likely to speciate, but we haven't really talked about that one yet. Which of the following human actions is most likely to improve the long-term survival of the amphibians? Well, if you could somehow get them to get together, that would be good. Cloning the largest individuals to counteract the effects of aggressive predation. Well, I don't know. Are the largest ones more likely to get preyed on or less likely? That is, I don't know. There's not enough information to say whether something like that would help. And probably cloning a bunch of them is a little bit more than what we're going to do. Reducing the population size by 1/5 to decrease competition for limited resources. Nope, they will reduce their own population, so that's a no. Constructing a dam and irrigation system to control flooding. Yikes, you probably will have less wetland then and they'll die off. Building ponds in areas of dry land to promote interbreeding between separated populations. That is, that's what's going to do it for us. So if you can build a pond here and here and here, and now they can hop between the areas that they live in, then maybe they can interbreed, and that might help save this species. Okay, number 9. In the Arctic Ocean, the predominant primary producers are phytoplankton. So phytoplankton are like plants, right? Phytoplankton are consumed by zooplankton, which in turn are eaten by codfish. In the years when there is more open water, less ice coverage, there are more zooplankton and fish than in years with less open water. So more water means you have more zooplankton, more fish, probably because with more open water, you get more phytoplankton. That's the only reason that you would be increasing the folks that eat these. Based on the graph above, this difference is mostly because, okay, so number of months with open water. So if you have open water a lot of the time, it looks like you have more primary production. So the more open water, the better the phytoplankton do. Less open water, the less well they do. When there is less open water, light is blocked from the zooplankton, so they cannot produce as much food. Zooplankton do not produce food. Boom. So that's wrong. When there is more open water, the temperature is warmer, so the zooplankton and fish populations increase in size. Well, maybe, but they're going to need something to eat. The ice blocks light, so in years when there's more ice coverage, there's less photosynthesis by the phytoplankton. That's what we're looking for. Here's your answer. So if you have more ice coverage, less photosynthesis, and that's what this shows. So open water is the opposite of ice coverage. So more ice coverage, right? That's what it says. More ice coverage would be over here. That would mean less open water, right? More ice coverage. And that means you're going to have lower productivity. Ice increases the light available for photosynthesis. That makes no sense. So primary production increases. So that's backwards again. So one kind of tricky thing about this is that it's saying number of months with open water, but you have to think of this the opposite way, number of months with ice coverage. So the more open water you have, the less ice coverage. So APBio does tend to really enjoy doing that. They'll talk about ice blockage or ice increases, which is the opposite, right, of open water. So that's one of their favorite modes, one of their favorite things to do.